This conference will now be recorded.
Okay, so it's 9:02, so let's slowly get started. Um, so I talked about random multiplicative growth, and I'm going to continue talking about this today. So I told you about independent growth, uh, objects growing independently from one another. Nothing much happens except that if you're looking at a system of a large number of non-interacting growth, uh, objects growing, then I told you that there's this interesting concentration transition. After a while, the Halfindel index of, for example, if you think about cities in a country, the Halfindel index of these cities will become non-zero, even in the large population size, in the large country size. And in order to illustrate this, I promised to show you something last time, but I couldn't, so I'm going to do it today, which is an illustration of this concentration phenomenon. Okay, so this is the graph I want to show you, the upper graph here. So usually I talk about this graph as the story of the grocer versus the jeweler. So what am I plotting here? So on the x-axis is the number of items that's been sold, either by the grocer, that's going to be the black line, or the jeweler, and that's going to be the red line. And what I'm doing here is I'm imagining that each item that is sold has a price that is distributed according to a power law distribution with some index mu. And so what I'm plotting on the y-axis is the total sales after having sold end products, okay? So on the y-axis here, you have the total sales after having sold end products on the x-axis. And so the black line corresponds to mu equal 2.5. So this is numerical simulations. And mu equal 2.5, you remember, means that the underlying distribution has a well-defined mean and a well-defined variance. And in this case, the central limit theorem holds, and actually the law of large number holds. That's what you're seeing in action on this graph. And what the law of large number means is that the total sales is going to grow linearly with the number of items sold. And the slope of this black line is just the average price of the of items in the grocery store. And what's in a sense interesting to realize, although it's trivial, is that this is not exactly a straight line. There are fluctuations, but you don't see them by the eye. Here, there are a total 10,000 objects that are sold. And on this scale, it looks like a straight line, although we know that there are fluctuations. There are fluctuations of order square root of n, but you don't even see them. And so the grocery store is a place where you can find objects that are a little more expensive than others, like, I don't know, a bottle of champagne or caviar or things like that, but it never goes very far, right? And the jeweler, on the other hand, I'm assuming he has a distribution with power law with index mu equal 0.5, so less than a half. And in this case, the graph looks completely different. So this is the concentration effect. And the concentration effect is that the whole total sales after 10,000 items sold is dominated by the largest one. More than a half of the total sales is due to this single sale here, which might be, I don't know, at a jeweler, you can find unique gems that are incredibly expensive, actually 10, 100, 1,000 times more expensive than the things that you sell every day. But what I want you to realize is that this is a scale invariant curve. This is sometimes called a devil's staircase because there are steps of all sizes. And if you zoom, for example, on this region here, you have the same dominance effect the fact that even on this little scale here, you see the big jump here is going to dominate the picture. And even if you zoomed here, where you think that there's nothing, but actually the jeweler has been active even in this region. And if you did zoom in this region, you would see exactly the same statistical picture, that is domination of extreme events. And so this is, visually what it means to have a non-zero Hafendel index. It means that some big chunks of the sum are realized by single events. Okay, so that's what I wanted to share with you. And now I'm going to go back to the screen, sharing. Okay. Okay. Any question about what I just said, or about something that I said last time and that someone would like to go back to? Okay. So as I said, what I talked about is independent growth and concentration. Now I'm going to introduce some interaction between these growing objects, and I'm going to call this interaction redistribution. So this is going to be a general word to say that growth is going to happen, within different objects, but sometimes the result of that growth is going to jump, so to say, from one object to the other. So let me write down the equation I have in mind, and then I'm going to comment what I'm writing. So remember, Zi is the thing that's growing. And so think of it as the population in city I, Zi. And so what I wrote last time was something that was mi plus eta I of t Zi. So this is what I've called growth. This is multiplicative growth because it's proportional. Everything here is proportional to Zi. So this is the mean growth rate of city I. This is the random part, taking into account health conditions or whatever. And now what I'm going to add to this equation is some coupling between cities. So, it's very natural in the context of cities that people, of course, they have children and the population grows, but they can move from one city to another, right? And so what I'm going to assume is that the more people you have in a given city, the more probable it is that some of these people will leave and go elsewhere. So what I'm going to write is a transfer term. So sum over j of j little j to I zj minus sum over j of j I to j zi. Okay. So this is transfer, people moving from one city to the next. So ji is the probability per unit time that someone living in city j moves from j to I. Okay. And the same here, this is the probability per unit time that someone in the city we're looking at, I, moves from I to j. Okay. So this is a very general equation because I haven't specified what this matrix Jij is, and I'm going to say more in a second. But imagine another framework for this equation, which would be the growth of viruses with a certain type. So I would be the type of a virus, very appropriate these days. And so viruses can grow or disappear, hopefully, at an exponential rate, but they can also mutate. And so these would be mutation rates, okay? And you can mutate from J to I, you can possibly mutate back from I to J. And so this is a model for mutation, if you want. In terms of wealth, I is an individual, Z is its wealth, so there's a growth term. And then by trading, part of its wealth or her wealth can be handed over to other individuals, or vice versa. He can get richer by getting the wealth of others through trading. Okay? So of course, this is a very naive model, but let's assume that this is something like that happens. And the basic question I'm going to try to ask today is, how does redistribution affect condensation? Okay, I'm writing this question in full because this is going to be the main topic of today. So let me frame this again for you. You remember that without these transfer terms, okay, I've shown you that this independent growth processes, at some point, there is this concentration transition. Okay, I said that beyond some critical time scale, the Hafindel index is going to go from a zero value to a non-zero value. And so if there's no transfer, the longer you wait, the more probable it is that you will get concentration or condensation. So now, intuitively, it seems that if you allow for redistribution, mixing, if you want, if you allow for rich guys to spend their money and enrich poorer guys, if you allow large cities to spill over and have people moving to smaller cities, then maybe you can avoid this condensation effect, okay? And so what I'm going to show to you is that it's actually quite interesting, because depending on the conditions, you can avoid condensation, or you still get condensation if the transfer rate is small enough, okay? So that's what I'm going to talk about today. So, of course, this model is completely general, and there's little you can say about it, except one thing, which is that these transfer terms, they conserve mass, okay? So let me write it here, mass conserving, mass conserving. So what I mean by this is that in the absence of growth, okay, if I didn't have any growth, then you can show, it takes really 1 minute, that in the absence of growth, if I sum over all i's, this equation, so sum over I of dzi dt, then I find 0. And the reason is that, you know, the total number of people going from j's to i's are going to compensate the number of people going from I to j's on average over all cities. I mean, in words, it's pretty obvious that moving people from one city to the other doesn't change the number of the size of the population, but you can show it formally. So these terms are mass conserving, whereas this one obviously is not and contributes to growth of the population. Okay. So as I said, apart from this general observation that these terms are mass conserving, there's little you can say about this equation in full generality. So one has to make the model a little more specific in order to say anything. So I'm going to give a few examples and tell you more about these specific examples. So one example is what people like to call, in particular in physics, the fully connected case. And this amounts to say that ji to j is equal to some j0 over n.
Sorry, just be careful, you're going out of our scope.
Okay. So let me check where I am. Okay, now you've seen the outline. I'm going to go towards my line. Okay, thank you. So what does this mean? It means that there's sometimes this transfer rate is also called a hopping rate. So this transfer rate or hopping rate is the same independent of the starting point and of the end point, and it's equal to a constant J0 divided by n, the total number of sites. So I'm going to specify the fact that there's an n here that I've also talked about last time. The same notations as last time. And the 1 over n is going to be needed in order to have a well-defined model in the limit when n goes to infinity. And the reason is because you can go anywhere. If you're in city I, you can go anywhere to any other city j. The total hopping rate, if you want, is n times j0 over n, so it's j0. So it means that the total moving rate from one city to the next remains constant in the limit of large countries. So this is a very simple framework, corresponds to what in statistical physics model is called the mean field limit. And of course, in this case, when we are going to be able to solve the model, and that's what I'm going to show you in a second. Another possibility is to have a random graph with the same j for all links, but apart from that, something that's random. So let me draw something that looks random. Of course, it'll be more complicated than this. So every node is a city, and every link is a link. And in principle, one should also specify a direction, because maybe there are jumps that are possible from I to J and not from J to I. Okay. So that's another case. And the last case on which I'm going to say a lot is regular graphs. So for example, you could have a two-dimensional lattice like this. So each node would be a city again, and each link corresponds to a possible hopping rate. So this means that there's only nearest neighbor hopping, and it could be a model for population spreading. So imagine that we're in ancient ages, and people can only move locally from one site to a nearby site. And in this case, we would describe with this equation random growth of tribes, and the fact that tribes can move by walking distance from one site to a nearby site. So okay, this is again a very simplified view, but you can keep that in mind. And of course, you can imagine many more complicated things, because here, what I'm saying by random graphs or regular graph is the topology of the JIJs, but I'm still going to assume that there's the same value of J0 on all the links. Okay. So I'm neglecting the fact that the J's can also be link dependent. So there's a whole variety of models that you can encapsulate in such a framework. Okay. So what I'm going to consider first here is the mean field limit, because you're going to see that it's interesting in itself, and we'll find a first conclusion about the role of redistribution on condensation. So I'm going to assume for now that all the mi's are equal to m. So sites are growing at the same average speed, average rate, m. Of course, there are fluctuations that are independent, but the average rate, the average growth rate is the same. And I'm going to introduce something that is quite natural, which is the average value of z at time t, which is defined by 1 over n sum over I of zi. And of course, the mean field will correspond to n going to infinity. Okay. So let's look at the general equation for the choice I'm making here. So mean field is corresponds to jij equals j0 over n for all I and j. So let's see, for example, this term here, you're summing n terms that are all equal to j0 over n. So this last term is just minus j0 times zi. And this term here is j0 over n, sum over j of zj. So this is exactly j0 times z bar, okay? So in this limit, or in this case, the equation on zi decouples, or actually it's only coupled through the mean of z, but it's not explicitly coupled to individual j's anymore. It's the same z bar that couples everybody. So it's equal to m plus eta I of t zi plus j0 z bar of t minus zi of t. Okay. So again, this term here comes from that one, which exactly reproduces this object, and this term is that one. Okay, so that's the equation I'm going to study now. Remember that I'm going to choose for now the Stratonovich convention. So the Stratonovich convention, you remember from last time, it is to assume that eta I of t, eta I of t prime, or eta j of t prime even, is delta ij, so growth is independent from site to site, times sigma squared over 2 tau c, exponential of minus t prime over tau c. And so I'm assuming that there is a finite but very small correlation time that allows us to deal with these equations as if eta I was a regular function. Later on today, I'm going to speak about another problem where I'm going to use the Ito convention, because it will be more natural to think in that case of the process as with zero correlation time, as completely independent from one time step to the next. But for now, as I said last time, I'm going to keep this simple way of dealing with this process. So, for example, this equation here, you see it's a linear equation for all zi given z bar of t. And so the explicit solution is zi of t equal j0 integral from 0 to t, or to minus infinity to t, dt prime exponential of m t minus t prime minus j0 t minus t prime plus integral from t prime to t dt double prime eta I of t double prime, everything acting on z bar of t prime. Okay, so all this is in the exponential, and this is the solution. This is a general solution of a linear differential equation with a non-zero right-hand side. Okay, so don't worry too much. You can redo it quietly. But the only reason I'm writing this explicitly is that from this thing you can actually derive by summing it over all i's. So if I sum here this thing and divide by n, you see I'm going to sum here and divide by n, and I can get a closed equation in the limit when n goes to infinity. I can get a closed equation on z bar, because essentially this term will average out. I'm going to average sum over I of exponential of these terms, and it's going to be okay in that case. And so all this to say that I can find, with a little work, that z bar of t is z bar of 0, the initial condition, exponential of m plus sigma squared over 2 times t, and that's when t is much greater than tau c. Okay. So what I'm finding in this model is that the total population size, or the average population size, up to a factor n, is growing exponentially at a rate that is not exactly the average rate m. It's given by m plus a sigma squared over 2. So there's a little bit of the fluctuations that help the total population to grow a little faster. Okay? So, you know, when m is positive, it means that the population is growing forever. And so superficially, it means that there's no stationary state, because it means that, you know, the whole thing diverges to infinity. But so in order to get a stationary state for the population sizes, Zi, I'm going to do something very natural, which is to rescale the population of a city by the average population size. So what I'm going to introduce is this quantity small cap Zi equal capital Zi divided by Z bar. Okay. And so intuitively, again, the logic is that the population size is, you know, diverging with time. That's what I've just shown you here. But if I rescale the population in each city by this average population size, then maybe, and that's what we're going to show now, maybe these rescaled quantities have a well-defined distribution in the large time limit. Okay, and that's going to be the stationary distribution I'm looking for. So if I look for the evolution of Zi, so dZi dt, this is going to be equal to 1 over Z bar d capital Zi dt minus Zi over Z bar squared dZ bar dt. Okay. So here I'm using the equation for Zi. Here I'm using this equation here. And so finally, what you get is an equation for dZi dt, which is eta I of t minus sigma squared over 2 Zi plus J0 1 minus Zi. And you can guess where all these terms are coming from. Eta I small zi just comes from here. 1 minus zi it comes from here. And then because of this term here, the small m contribution has disappeared, and there's an extra sigma squared over 2 coming from here. Okay. Okay, so now I get something that has a chance of having a well-defined stationary distribution for large times. And in order to show that more clearly, what I'm going to do is to introduce a new variable. From Zi, I'm going to introduce something that you will see helps a lot, which is a log of Zi. Ui equal log of Zi. And I'm going to derive an equation for dui dt. And now, again, take just 1 minute to remember that what I told you is when I have a Stratanovich convention, it means that change of variables are allowed. Allowed in the sense that they are trivial, the usual rules apply. The chain rule applies for differential equations. And in the Ito convention, the change of variables are allowed, of course, but you have to be careful in the sense that there's an extra contribution that would change the equation. Okay, so just as an illustration, dui dt, this is, as usual now, we can do as usual, is d log zi dt, so it's 1 over zi dzi dt, and there's nothing else because it's a Stratanovich convention, and so you just have to divide by zi this equation, and it gives. So I shouldn't go too far in that direction. Let's use the room I have here. So dui dt, using the fact that it's just 1 over zi dzi dt, it's equal to eta I of t minus sigma squared over 2 plus J0. So 1 will become 1 over zi, okay? And 1 over zi is exponential of minus ui. So exponential of minus ui minus 1. Okay? And now I'm happy because this is a standard Langevin equation. And we know everything about Langevin equations. So this describes the motion of a fictitious particle driven by a certain force. The deterministic part of this equation is usually called a force term. And then there's a temperature term, a fluctuating random term, eta, which plays the role of temperature. So we know that this is describing a particle in a given potential, which is driven by thermal noise, and the equilibrium solution will be the Boltzmann wave. So let me be more explicit. So the equation for u, I can write as du dt equals minus dv du I plus eta I of t, okay, where v of u with v of u, so it's just the term I need to introduce to see this as the derivative of a potential, and it's given by J0 exponential of minus u plus J0 plus sigma squared over 2 times u. Okay. Clearly, if I take the derivative with respect to u, I'll have a J0 plus sigma squared over 2 with a minus sign. So these are these two terms. And then I have the J0 exponential of minus u from here. So as I said, what does this describe? It describes the thermal motion of a fictitious particle. Of course, here we're not speaking about particles, we're speaking about population sizes rescaled by the average population size, or wealth rescaled by the average wealth. But let me think of this equation as a Langevin equation for a particle in a potential. So what this potential looks like, well, for very large U positive, this goes to 0. So it's going to grow linearly with U.
We don't see what's on the left.
Ah, okay.
See you now.
Let me see what you're not seeing.
Just
Okay.
before the equal sign.
I'm just going to change it for, then you'll have to remind me.
Thank you.
Okay. Thank you. So du dt minus dv du plus eta I, this is the Langevin equation of a particle in a given potential. And what I'm drawing here is v of u. So asymptotically, for a very large positive u is growing linearly. And for very large negative u, then exponential of minus u becomes exponentially large for u negative. And so it's going to grow like this. So if I'm drawing the actual potential, looks like this. Okay. And so, intuitively what's going to happen is that this thermal particle here, it just hovers around the minimum of the potential, but sometimes it's going to be able to go uphill here and reach reasonably high values of u. But because the potential is growing extremely fast there, it's going to have a hard time going for u negative. Okay. But very more precisely, what we know is that the stationary distribution, the equilibrium distribution of u, is nothing but the Boltzmann weight. So it's a certain normalization, n exponential of minus v of u over temperature. And here temperature is sigma squared over 2. So it's exponential of minus v of u over 2 sigma squared. So this is a stationary distribution. If you're more greedy and if you want to know what happens at finite time, how fast do you reach this stationary distribution, you can do it. You can do it thanks to the so-called Fokker-Planck equation. So to each Langevin equation, you can associate an equation describing the evolution of the probability to find a particle at u at time t. And I'm not going to derive this Fokker-Planck equation, but you'll see that also in the TDs. And if you look at the lecture notes, the Ecole Polytechnique lecture notes, you'll see a derivation of this Fokker-Planck equation. But the general shape of the Fokker-Planck equation is, for the Langevin equation I just wrote, is d by du dv by du p. This is called the drift term. This comes from this deterministic fourth term plus the so-called diffusion term, the term that comes from eta, the Langevin term, sigma squared over 2 d2p over du squared. So let me put this in. So this is called the Fokker-Planck equation. And you see, in principle, it allows you to solve for the full dynamics of P of U. So if you start by a P of U at time t equals 0, then you can evolve the probability through this Fokker-Planck equation. And what you'll find is that for very long times, the probability distribution settles to this Boltzmann weight. And if you want to do it quickly, you can check that if you inject this shape of P equilibrium here, you find that this term is 0. So that dP dt is indeed 0 at equilibrium. So the Fokker-Planck equation is a very useful formalism, and I'm going to use it several times later on in these lectures. Okay, so how far can I go to the right, or maybe I can shift the camera back. Okay, so I have my P of U. Now, of course, I'm interested in not in U, but in Z. But essentially, I'm done, because once I get P of U, I get that P equilibrium of Z, the stationary distribution I'm looking for, the rescaled population sizes or wealth. This is just given by P equilibrium of U du dz with U equal log Z. Okay. So if you remember, I told you that what I'm calling P of Z means the distribution of Z, and it's not the same function as P of U. Although, as I said last time, this is a little bit an abusive notation, but a very convenient one. Okay, so if I put everything together and inject here V of U and make the change of variables, then what we find is that the stationary distribution of Z is a certain normalization coefficient that I'm not going to care writing down. Of course, one can compute it. Exponential of minus 2J0 over sigma squared Z divided by Z to the 1 plus mu, with mu equal 1 plus 2J0 over sigma squared. Okay, so what do I get here? I get exponential of minus 1 over Z on the top and a power law on the bottom. So if I plot here P of Z, the equilibrium of Z, what does this look like? Well, for Z very small, very close to 0, this is exponentially small. This is an essential singularity at Z going to 0. So it's very, very flat here. Then it goes like this. And then for very large Z, this becomes 1, okay, because 1 over Z goes to 0, and you get a power law. Okay, So that's nice, because this calculation can be done to the end, as we just did. And the conclusions are quite interesting. First of all, what we get is that we've generated a power law distribution. Okay, there is a stationary state. Once I work with rescale variables, don't forget that I've rescaled Zi, capital Zi, by the average wealth. So I'm on the correct scale, comparing apples to apples, if you want. And on that scale, I get a stationary distribution where the probability to have a very small city sizes or very poor people is very small. Then there's a hump. And then there's a very long tail to the right, saying that there is an appreciable probability to get very rich people or very large cities distributed with a power law. And we have an explicit value for the power law index, which is 1 plus 2J0 over sigma squared. So this is a mechanism leading to power law distribution. Note that A, mu is not universal. Okay, so we have a power law that's continuously dependent on the value of the parameters. And okay, this is a model that gives you something that leads to non-universal power laws. There's nothing critical in this model. There's no critical point. And so we have a power law, a scale-free phenomenon without any phase transition or critical point. Usually when there's a critical point, the value of mu is universal. And we'll see examples of that later on. But in this case, actually mu is not universal. So if you remember, for example, the Pareto distribution for wealth is remarkably stable over time and over countries. And so if we believe this model, we would have to understand why the ratio J0 over sigma squared is so common to different types of economies. So, okay, maybe there's an argument for that. Maybe we're not on the right path. Actually, it's still very much an open problem as we speak. I'll comment that a little more in a second. The second remark is that mu is strictly greater than 1 for J0 when J0 is greater than 0. So that's interesting too, because you remember that mu greater than 1 means that this distribution has a finite mean. And so in this case, as soon as there's a little bit of redistribution, as soon as this J0 is non-zero, it's present, it can be as small as you want, provided it's positive, then provided there's some kind of redistribution, the final distribution of wealth or population has a finite mean, which also means that the Herfindahl index goes to 0 for large n. Okay? So no condensation. Are you still seeing this? Yes. So this is strange, right? Because in the absence of J0, I showed you last time that this independent growing cities are going to condense at one point. There's a time TC that I call TC beyond which the population is condensed in a few cities or the wealth is condensed in a few individuals. As soon as you add a J0 term in the mean field limit, again, I'm in the mean field limit, then you break this condensation and you get back to a kind of more democratic type of distribution. And the last remark, two more remarks, maybe. see. Okay, see. When J0, I hope you can still see this. When J0 is much less than sigma squared. So when the noise in the growth rate is much bigger than the exchange rate. By the way, dimensionally, sigma squared is a frequency like J0. So this is a meaningful comparison. Then one gets a zip floor, which corresponds to mu equal 1. And you remember that there's a lot of phenomena that are described by the zip floor. And this is a mechanism that naturally leads to a zip floor, provided you're in the limit of small redistribution. When this redistribution is weak, then generically you're going to generate with that model a zip floor. And so finally, if I take, reasonable orders of magnitude for if I really think of this model as a model for wealth distributions, then it is not completely ridiculous to think of this model as a kind of wealth tax model, because you see here the proportionally to your wealth, you're going to give away a part of your wealth, and it's going to be redistributed uniformly in the population. So in spirit, this is a kind of wealth tax. And so if I take J0 equals 1% per year, so you have a wealth tax that is 1% of your wealth every year that you give away to the taxman, to the state. And sigma is the variance of your investments. So sometimes you make more, sometimes you make less. And so if you take sigma on the order of 20% per year, in fact, the square root of year. So some years you do, say, 5%, other years you do 25%, and so on. Then you get that mu is around 3/2, which is the Pareto value. So there's a lot of problems with this model if you try to compare it to real wealth data. So it's clearly not the final model to describe what's going on to understand wealth distribution. But if you're adamant to use it as a model for wealth distribution, you see the kind of numbers that you get if you make a go at trying to be realistic. And so these are not completely crazy numbers. Maybe sigma 20% per year is a little too high. But anyway, that's in order to give you, that's just to give you a feeling of the type of numbers that you would get from this model. Okay. So that's the story of the fully connected model. And again, the story of the fully connected model is that there is no condensation anymore. So no redistribution, concentration transition at a finite time. Any small redistribution in the mean field model leads to no condensation. So what I want to tell you a little bit about is what happens in other cases. before I do that, okay, Valentina, great. So indeed, the Fokker-Planck will be derived in the next CD. So let me give you a few words on the other cases. So random graph. So for the general case of a random graph, must be specified, because random, what does that mean? And we'll see examples of random graphs later on in the lecture. So for example, the simplest random graph is called the Erdős-Renyi graph, where you draw at random the presence of a link or the absence of a link. There's also another type of graph, which are tree-like graphs. So for example, where each node is connected randomly to 3 other nodes. Okay. So this is a little zoom on what's called regular random graph. That are locally tree-like, but you might have loops in such a graph. So for example, this guy here might be connected to these 2 ones, and then okay. So this is a random regular graph, in the sense that sites are connected randomly to other sites, but each site has a fixed connectivity. Okay. And so the connectivity is sometimes called C. So here in my example, C equals 3. And the fact that it's a locally tree-like graph allows you to make exact calculations. And what you find in this case is that when sigma squared over J0 is less than a certain critical value that I'm going to call A critical, then there's no condensation. Half-spindle is 0. And if sigma squared over J0 is greater than a certain A that depends on C, then H is positive. So you see, now we have a new type of result, because what I got is up to now either always condensation, that was the case of independent growth, or never condensation, that's the case of the fully connected graph. I can have an intermediate situation where you have sometimes no condensation and sometimes condensation. And what matters is this ratio sigma squared over J0, the same ratio as this one. And so what you intuitively see is that if J0 is large enough, you avoid condensation. If J0 is small enough, you are condensed. So this is a case where there's a true phase transition in this model. So if I plot, again, just to be pedantic, because this is just reformulating what I just said. So if you plot, for example, as a function of J0, the half-spindle index, what you're going to get is that for large enough J0s, if there's enough redistribution, the half-spindle index goes to 0. So it's going to look like this. And then when J0 becomes too small, it's going to increase and tends to 1 when J0 goes to 0. And this is for a fixed value of sigma squared. So for a fixed amplitude of the noise, you need to redistribute forcefully if you want to avoid extreme condensation, okay? But it's possible. So if you want, in order to understand the previous limits, in the case where J0 is 0, that is, if there's no redistribution, this is the independent growing population model. This is the model that I talked about last time. And we know that at long times, the Huffindel index tends to 1. So we recover the previous result. And if you're in the mean field model, that is, if sorry, sigma squared over AC. So in the mean field model, AC goes to infinity if you want. And so this shrinks to 0. And so there's no condensed phase anymore. So that's how you recover the mean field limit from this model, is that in the limit C goes to infinity, AC also goes to infinity. So condensation disappears in this limit, okay? So this is an example of a random graph, but this is a generic conclusion. Yes, I'm finishing and then you ask your question.
Sorry, okay.
So this is a generic conclusion. For these random graphs, more complicated, there's, in general, a phase transition between a condensed and a non-condensed phase. Yes, please?
So here we're looking at the limit n tends to infinity. What happens in the case of finite n?
Well, you know, the fact that there's a phase transition only exists when n goes to infinity. If n is finite, all the statements I made are only approximate, because, for example, you know that if you're in a non-condensed phase for finite n, the non-condensed phase means that the Huffindel index is of order 1 over n. So it's not 0. So there's nothing that you can say, you know, mathematically, rigorously. You have a crossover between a regime where h is of order 1 over n and a regime where it's of order 1. So if you want, if I plot again my phase diagram for finite n, so if I do Huffindel index as a function of J0 for finite n, then instead of having the nice true phase transition regime where I have this line, okay, with a true point separating a region where it's 0 from a regime it's non-zero, then for finite n, I will have something like this, right? So it's going to be a crossover. So you can ask interesting questions. You can ask, okay, so how does this point here, how does it go to 0 as a function of n? If I'm right at the transition, but at finite n, then this will go to 0 with a strange power of n, whereas these points here will go to 0 as 1 over n. And these points won't go to 0. So there are interesting questions to ask, but you know, in terms of this, the existence of a true phase transition, it's only well defined for n going to infinity. But of course, it's enough for many purposes because you know what the system is going to behave like. Okay? So now, regular Euclidean lattices. So D equal 1, this is just a chain. Okay. D equal 2, it would be what I've drawn before, something like this. Maybe more complicated cell structures, but essentially something like this. And then D equals 3, you can think of as a cubic lattice. And so on. Okay. And you can also, if you want, formulate this model in higher dimensions, although it may not have such a clear physical motivations, but it can be useful from a theoretical point of view to think of higher dimensions, and it's also useful in non-physical contexts to think of these extended problems. So now what happens? So it's that's where, if you were in the class, it would be easier, but what's your guess? What's going to happen? So does anyone have a guess for D equal 1? I agree that this is a complicated exercise being remote, but is there any suggestion?
Sorry, can you hear me?
Yes. Yes.
For D equal 1 is like having a tree with a very low connectivity.
Yes. Exactly.
So this will obtain the same as before.
Right. Well, in this case, it is the case that the AC goes to 0 when you only have two neighbors like this, and you're always in a condensed space. So you're right. This is a random regular graph if you want to see it that way, but the value of AC goes to 0. So if you remember the graph that I removed, that I erased, it means that the transition goes all the way to J infinity. And so for any finite J, you're always going to be condensed. So that's quite interesting. It means that it's not only the strength of J that matters, there's also something about the topology of the graph that matters. And in the case where you have a one-dimensional chain, you'll never get away from condensation. Okay, at long times, you are actually always going to be, and in fact, it's extreme condensation in that case. So I should call this extreme X condensed, extreme condensed in the sense that H is equal to 1. Okay, so at long times, whatever the value of J0, you'll never get away from a few people or a few cities condensing the whole population. It's not completely intuitive that there's not enough mixing if you want. You think of that as mixing, as stirring the brew. And if J0 is very high, but you have a one-dimensional chain, well, if you wait long enough, doesn't matter. You're still going to get everybody at the same place. Okay. So there's a little bit of a surprise here, but it's an interesting surprise. And actually, as I'm going to mention, the one-dimensional case has become one of the most important models in theoretical physics in the last few decades. But I'm going to go back to that in a second. So D equal 2, well, again, you get extreme condensation. So it's a little more subtle in the sense that at finite times, you need to wait very, very long times in order to get, H equal 1. But asymptotically, as a mathematical statement, D equal 2 is again a case where you get extreme condensation. So there again, mixing is not strong enough if you want. And the reason, if you intuitively, is that you always go back to the same place in D equal 2. If you make random walks on a two-dimensional lattice, or on a one-dimensional lattice, you always go back to your initial starting site. And the fact that you always revisit the same sites prevents the model from avoiding condensation. But for d equals 3, things change, and d equals 3, there exists a critical value of jc, for a given sigma squared, such that for j greater than jc, j0, then you're not condensed. And if j0 is less than jc, h is positive. Okay. So you see that the phenomenology is quite interesting, and depending on not only the strength of redistribution effects, but also the topology of the lattice or the graph, you can get various situations. Okay. So this is a description, a very rough description of what's going on, but let me show you why this model in Euclidean space is actually related to a whole family of models that have attracted amazing attention in the last 20 to 30 years in the mathematical and theoretical physics community. So that's what I'm going to discuss here now. Link with other problems. And that's going to be a segue into my part 4. And of course, you don't see part 4 anymore. Which is optimization and Hamilton-Jacobi-Bellman methods. Okay, so where does that come from? So I talked about redistribution and growth, and I'm going to end up speaking about optimization. And interestingly, it's the same formalism, it's the same equations that can be interpreted in different ways that I'm going to chat about now. So let's look again at the equation I wrote. dz dt, dz I dt. There was a random term, m plus eta I zi plus sum over j of jij, jji, zj minus sum over j of jij, zi. Okay. Now let me put this model on a regular lattice, the types of lattices I've just talked about, with each link here. So this is I and j. I and j must be nearest neighbors. And if they are nearest neighbors, then ji to j is equal to j0. Okay. If I and j are nearest neighbors. Okay. So let's look at what it looks like this term in this case. Well, you have two indices to define where you are in a two-dimensional lattice. So I'm going to introduce a notation which is that the position on the lattice is a vector each component of this vector taking only discrete values, okay? So this is a 2D vector with only discrete values, telling you where you are on the lattice. And what you get if you expand this term here is for a given x, that is a given I now becomes a two-dimensional vector if you want. So I becomes x. Then I have that the second term is minus 4 z of x, okay, because there are 4 neighbors, so minus 4 j0 z of x. This is this term here. And this term is going to give me z of x plus 1 in the okay. So this is the x direction and the y direction. But I'm okay. Maybe I should call this r and not x, right? R. Okay, sorry for this change of notation. So I need some space. So this term here is going to be j0 z of x plus 1x plus z of x of r plus 1x, z of r minus 1x plus z of r plus 1y plus z of r minus 1y. Okay. And of course, 1 in the direction of x is this vector, 1x, and 1 in the direction of y is this vector. So now imagine that z is a smooth function, is varying smoothly over space, over R. Then I can Fourier expand, sorry, not Fourier, Taylor expand this expression here. And I guess that you won't be surprised to see that the first term is 4 times z of r, so it goes away with that one. The second term vanishes, and what you get in the end is a Laplacian term. So this equation in the continuum limit. Okay, so I was just guiding you to see how it works, but I'm sure you've done that somewhere in your curriculum before. But if you do this Taylor expansion, then this discrete equation for redistribution becomes a continuous equation, which is dz of r and t dt equals m plus eta of r and t. So now you have a noise term that depends on where you are in space times z of r and t. And then the term that I labored on trying to convince you that you had a Laplacian coming from the Taylor expansion is going to be plus J0. If you want to be okay with physical dimensions, I should also introduce the lattice spacing A. So A is the actual physical distance between two sites. And what I get is J0 A squared times the Laplacian of Z. of R and T. Okay? So let's reflect on this. We have a term that is just a diffusion term. This is, if I didn't have growth, I would have a pure diffusion equation. Heat, also called heat equation. And now on top of the heat equation, I'm throwing in a term that describes random growth. So it's very physical what we get. We get a population on around site R and T that grows randomly and diffuses in space. And this is exactly what we try to capture with this equation. So it's not a surprise, it's just a continuous limit of this equation, of the first equation, is this second equation, which I'm going to give a name to. I'm going to call this equation A, because we're going to see it again in another context. So this equation is extremely important, and it has various names in the literature. So for example, it's called the stochastic heat equation. Stochastic heat equation, for the reason I just said. There's the heat part and the stochastic part. It's also called the parabolic Anderson equation. The reason is that this looks like a Schrödinger equation a little bit with a random potential. So of course, in the case of quantum mechanics, you would have an I here, okay? And Z would be a complex object, so the wave function. And then this would be the Schrödinger equation for a particle in a random potential. And perhaps some of you know about this problem. This is called the localization problem that was invented by Phil Anderson in 1958 and is a hugely important part of solid state physics and describes what's called Anderson insulators. So surprisingly, the physical story is that the particle in the random potential can be completely localized and never go away to infinity. So it cannot carry electricity, for example, such an object. So you can have localization just because of randomness. And in a sense, although technically it's different, in a sense, this is similar to the condensation problems that I've talked to you about. Instead of finding the particle anywhere in space, the Hafindel index of the wave function, which in physics is called the participation ratio or the inverse participation ratio, is non-zero in certain cases because the particle cannot escape to infinity. And so it's very related. So if you want, this equation is the Schrödinger equation corresponding to Anderson's problem without an I. And of course, this changes a lot, but it explains the name parabolic Anderson equation. And as I'm going to allude to later on, it's also related to what's called the KPZ equation. After three theoretical physicists, Kardar, Parisi, and Zhang, that, as I said, has become one of the totem equations in theoretical physics. And in particular, if you're in one dimension, so if instead of two dimensions, like my drawing here, you're on a chain, then the KPZ equation is exactly solved. and I'll quote some of the results later on. So you can have an exact solution for this stochastic heat equation, exact in a sense that has to be defined, but everything is known about this problem in one dimension. Okay, so now I'm going to move to part 4, optimization and Hamilton-Jacobi-Mailman, and talk about something that superficially seems completely unrelated to what I've talked to what I've just talked about. And this is a little bit the magic of mathematics, if you want, or theoretical physics, as you wish, to be able to map problems that superficially have nothing to do with one another and get inspired from the solutions of one to say things about the other. And in passing, I hope that you will learn something that is rarely discussed in physics curricula, whereas it's hugely important in other fields, in particular in economics or in certain parts of engineering. So what I'm going to talk about now is part 4. Let me switch back to right. So of course I won't be able to finish everything today, but I'm going to speak about optimization and Hamilton-Jacobi-Mailman. Okay, so let me introduce you to a kind of fun game, a treasury hunt. Okay, so what I'm drawing here is time in this direction and x in that direction. Okay, and so you're on a bike. Think of yourself on a bike, and you're on a bike, but along a road, a one-dimensional road. So there's a one-dimensional coordinate that describes your position. And what you have to do is to try to get as many bounties as possible. So I'm going to assume that in this space-time representation, there are what I'm going to call a bounty, so a reward if you want, that are randomly scattered. So they appear at random, or maybe they're deterministic, it doesn't matter. But they are objects that you should collect in order to improve your score. And you have to do that while riding your bike. So your trajectory is going to be a path. So this is your trajectory. Okay. And so you're pedaling in order to get as many bounties as possible, to have as high a score as possible. Okay. The problem is that you also pay some effort in order to bike fast. So, collecting bounties will come at a cost, and the cost is how fast you have to bike. So there will be an optimization problem here, which is to get as many bounties as possible while not paying too much in kinetic energy, if you want. So that's what the game is going to be about. And now let me frame it in a more mathematical way. Okay, but so if you or at least get the general idea at this point, it's good. It's a game. You have to collect bounties, but you won't be able to, fast enough to get all the possible bounties on the space-time trajectory. Okay, so how does it translate? So first, let me describe the trajectory. So the trajectory is given by your speed, dx dt, okay? And this dx dt is going to be given by the sum of two terms, one that you control and the other one that unfortunately nature or the person who has invented that game imposes on you. So what I'm saying here is that your speed is given by a certain velocity that you choose. So this is called sometimes a policy or a control. So that's what you control, okay? But unfortunately, as I said, there's a problem which is in the sense of a random noise. So as I said, it's not as easy as my initial description seemed to be, because on top of this optimization, there's wind, for example, the wind that blows and that speeds you up or slows you down in a way that you don't control. Not controlled. So this is wind. These are obstacles that are randomly scattered, and so you don't see them, and at the last minute you have an obstacle that speeds you up or slows you down. Okay, so that's the trajectory. That's a description of the trajectory. It's the line x of t that I've drawn here is just integrating this equation of motion. But the problem is that, the first problem is that there's a noise term that prevents you from fully controlling your actual velocity, okay? So what we're going to assume here for psi is an Ito noise. And I'm going to assume that psi of t up I'm going to assume that psi of t prime is equal to 2j0 delta of t minus t prime. Are you still seeing this? Hello?
Yes.
Yes.
Okay, you're still seeing this. Okay, fine. So I've introduced J0 here for a reason, of course, because it's going to end up being the same J0 as that one. But for the moment, I'm introducing J0 as the strength of this wind that bothers you. And here I'm assuming to start from the start that this is a delta correlated noise. And I'm thinking of this noise in an Ito sense. And if you remember what I told you last time, the Ito convention comes when you think of time as discrete. And so you're at t here, and the noise psi materializes after t. And so you cannot anticipate, you cannot predict anything about psi. You're always surprised by the next psi. So if you want to think of this that way, Ito is surprise, full surprise. Full surprise. There's nothing from the past that can help you anticipating the next time step. So that's, in these cases, you should use the Ito convention. And that's what I want to model here. I want to model you on a bike and things completely unexpected that happen. Okay. This also simplifies the discussion quite a bit. Good. So now what's your objective function? So I've said it in words. You want to accumulate as many bounties as possible, as many rewards, but you want also to spare your energy. So you don't want to overspend in kinetic energy. So I'm going to introduce the gain, curly G. So this is the gain. And this will have two contributions. One is the amount of bounties that you've been able to collect. So here I'm assuming that the game lasts for a certain time, capital T. Capital T is the end of the game. End game. And you see what this tells you is that you're going to gather bounties along your trajectory, along x of t. So the bounty that happens to be on your path at time t, you're going to collect it. Okay. So this is the total amount of bounties that you've been able to collect. And of course, you'd like this to be as large as possible. But as I said, the second problem on top of the noise is that you pay something if you want to bike hard, and what you pay, we're going to assume that it's proportional to kinetic energy. So integral dt v squared of x of t and t. Okay. Note that it's the part that you control that makes you pay something. At least the noise is free for you. I mean, you don't have to pay dx dt squared, you have to pay v squared. That's what you decide to do. And then if the wind helps you or if the wind is against you, it doesn't count in your gain function. Okay. So this is a typical optimization problem, a problem that in physics is called frustrated, because there are two opposing terms. One is that you would like to collect bounties that maybe are very, very far, and so you won't have time to collect them because you would have to bike extremely quickly. So there's this gain term and this loss term that kind of are conflicting and oppose each other. Okay. So the aim of the game is to determine the optimal policy. So the solution of this problem, if you want, the solution to my treasury hunt problem the solution that we are looking for is to find the optimal policy the optimal control, so what I can call V star of x and t, such that G is maximized. Okay. And of course, because there is noise in the trajectory because of psi here, G is also kind of random. So what we are going to look for is not the maximization of G, because G contains randomness, but the maximization of the average G average over psi. So you don't know what psi is, so you can't maximize something that you don't know. So the only thing that you can maximize is something that is averaged over the realization of the noise that you don't know. So that's what we're going to try to maximize, is the average gain average over the realization of the noise psi. Okay? So that's what we're going to do next time, because I won't have time to start this now. But before letting you go for 15 minutes, I want to tell you what is this treasury hunt game in different contexts. So, for example, there's a very important problem in physics, which is called pinning of one-dimensional objects. So in physics, as you know, there are point-like objects like atoms, but there are also extended objects like polymers or dislocations or vortex tubes in superconductors. There are also two-dimensional objects like membranes and so on. And often these one-dimensional objects, so think of it as the polymer, for example, it interacts with the environment, and often there are what's called pinning sites, and the object, the polymer, tries to minimize its energy, and the energy of a polymer is made of the interaction energy with the impurities. So this is pinning by impurities. And this V squared, in the language of polymer, V squared measure how costly it is to make bends like this, okay? So you're stretching the polymer, and by stretching the polymer, you pay some elastic energy. So this problem falls in the general framework of randomly pinned elastic objects, which has led to very interesting results that, as you're going to see, are related to things that I talked about. In particular, you remember maybe what I told you in the very first lecture. I told you about Barkhausen noise. Well, what is Barkhausen noise? It is the fact that in magnets, you have domain walls. You have domains where spins point up and domains where spins point down. And the separation between these domains are called domain walls. And you can think of these domain walls as kind of membranes. And these membranes are pinned by the impurities in the material. And so if the object is pinned, when you try to make it move, you have to, exceed some threshold. And once you exceed the threshold, the thing moves. And in the case of magnets, it creates a noise, which is called the Barkhausen noise. So the question is whether impurities will be strong enough to pin the object, or whether the object is going to freely move, not even if there are pinning sides, that it's free from pinning, and the object is actually free to move. And what you'll see is that pinning, what I'm going to explain next week, is that pinning, so the fact that an elastic object is not free to move, is the analog of concentration in the problems of random growth with redistribution. So this is, I think, a very spectacular analogy to think that, we spoke about concentration of wealth, and actually the question of whether wealth is concentrated or not in a society is mathematically related to the problem of knowing whether a polymer or a dislocation is pinned by impurities. So more about that next week. So I'm about on time. Maybe you have questions or comments or so if you want, those of you who want to make a break before Valentina starts at 11, right, Valentina? Oh, she must be on her way. I guess it's 11.
Yes, I'm coming upstairs.
Okay. So 11, Valentina. And so if in the meantime you want to chat, I'm totally free to do so. Don't hesitate to also contact Valentina or myself by email if you have questions or if you want to discuss. Because the problem, of course, is that I usually come at 8:30 in the morning when things are normal, and so people can get a grab of me and we can have a chat or a chat now. But since we don't see each other, this is not possible. So I think email or chatting now, if you want, is an option.
Yes, sorry. I'm not sure if I have understood what is the equivalent of the impurities in this specific problem.
Okay, so B of X and T is the bounty in my treasure hunt. And it's the potential energy, the pinning energy in the case of the directed polymer or the vortex. So if you want,
Okay.
every time the trajectory of this physical object now, which is not a trajectory, an abstract trajectory, this is a real physical object. Every time it goes nearby an impurity site, it gets some actual physical energy, which is B of X and T. So this is the energy. G, if you want, is a Hamiltonian now. So there's two parts in the energy. One part is pinning by impurity. So you want to be near impurities that lower your energy, that attract you. But there's a penalty, which is the elastic energy of the polymer, of the object, that doesn't like to be deformed, if you want. It would like to go straight. Okay. So if you want, what I'm saying here, and maybe I should have said that more explicitly, is that in my treasury hunt problem, T is time, whereas here, T is another spatial direction. So maybe, I'm sorry, that was clearly missing from my explanation. In the pinning problem, there's no time. It's a static problem. And what I'm calling T is another spatial direction. And this is X. But maybe it would be less confusing to call formally this Y, and then I would get, a pinning energy that would be X of Y and Y, and dy X of Y and Y. Okay, so B of X and Y gives you the energy of this guy, the energy of this guy, the energy of this guy, the attraction energy of these guys, and this is really the price you pay in terms of energy to make your object not a straight line, but rather bends all over the place. Is that more clearer?
Yes, totally. Thank you.
Okay. Yes, I was rushing a little bit at the end, and I should have been more careful with notations.
I have another question just about this. So
yes?
In the case where you consider the main walls in a magnet with impurities, what is then the cost you need? Because I guess the domain walls don't have an elasticity, but maybe it's the length of these domain walls which is minimized.
Okay. Right. So that's why I said that this problem is equivalent to pinning of one-dimensional objects. Two-dimensional objects, membranes or domain walls, they're more complicated because Y here becomes a two-dimensional object. Okay. A two-dimensional vector. So you should think of that as now a full surface that is bending up and down. And so in this case, you would have a d2y, two coordinates here, and v would be a two-dimensional object, which is the local slope of the d2y or dy, let me call it that. Y would be a two-dimensional vector. And what is v? V is it's a two-dimensional vector, which is the two slopes of your membranes locally. Okay, so I don't know if you see in space, but let me draw a two-dimensional object. So there would be one gradient in that direction and another gradient in that direction. Okay, so here I'm assuming that the surface moves up when you go behind the board.
Yeah.
And the norm of this two-dimensional gradient would be the equivalent of the velocity, and v squared now is the energy associated with bending it's the elastic energy associated with bending your membrane. Okay, you're creating more surface. You're creating more surface by having a membrane that's not flat, exactly as you're creating more length when you're considering a polymer that's not straight. Okay, and every piece of extra surface that you're creating costs an energy, and that's where it comes from.
Okay, thanks.
But of course, in the case of a two-dimensional time, so to say, this would be a two-dimensional time in the optimization problem. It's it's not natural to think of time as a two-dimensional object. So these two-dimensional objects lose the direct connection with the treasure hunt problem, if you want, the optimization problem. Okay.
Okay. Yeah, my question, but now it's clear, was that in the polymer you have the energy associated to bending the polymer, but with the domain walls, it's rather that you try to minimize the area.
Yeah, exactly. But it's the same. In the case of the polymer, you try to minimize the length. In the case of the membrane, you try to minimize the area.
Okay.
Sorry, I have a question as well.
Yes.
Could you give us maybe a list of references where we could find more details on the different topics?
So normally you have chapter 1 that has been given to you, and chapter 2, the one that I'm discussing now, is going to be given to you now. I'm going to give it to Valentina tonight, and it's going to cover everything on that I've talked about on redistribution. It won't cover this part on Hamilton, Jacobi, Bellman, because I haven't had time yet to write everything up. But I can certainly give you references to all these problems. Sure.
Okay, thank you.
Okay, good. Well, if you have any comments, any complaint, anything that you find useful for the rest of the lectures, please tell me or tell Valentina. Again, I mean, I think we're both here to make you as happy as possible. So we're clearly open to suggestions. Okay, well, have a good today, and yeah, okay, sure. Anyway, HGB I just started, so I'm going to go more in details next week. And as Valentina just said, you're going to have a today about this. Okay, goodbye then.
This conference will now be recorded.
Okay, good. Let me see the chat. Very well. Okay, so welcome back, everybody, to our to the session. So I don't manage. I would like to upload the text of the TEDs, which is the same one that I put on the folder, except that I just switch the order of the exercises, and I decided to talk in here about exercise number 3, or what was before exercise number 3, because I think it is more connected to some of the things that will come up in the future during the lectures. So now this exercise in the new version of the today is the second one, and the third one, which was about power laws, we leave it as a bonus exercise, and maybe if we have time at the end of this session, we can comment a little bit on what's in there. So before starting, as you see, I wrote just a little bit of summary about what we are going to do today. But before, is there anybody who has any questions about the previous today, or about the homework, or comments about the lectures? And just remember that in case you have questions which comes up during the way, you can just write them in the question and answer folder. That could also be comments about the speed of the lectures, the material, and so on, and we will process them during the week. Okay, so let's start with this today number 2. And this today in here is going to be about statistics and about inferring properties of distributions from data. So this might look a little bit disconnected with respect to what we had in the last lectures, but actually it is not. And in particular, I will make some comments at the end of the today, at the end of the second exercise, that will come up in the course of the lectures, in particular toward the end of the course. So stay tuned. And for what concerns the things that were discussed today during the lecture, so as I said, there will be the third today that will be about Langevin, Fokker-Planck, Stratonovich versus Ito, and stochastic calculus. So that will be covered in detail next week. And then the fourth today is about what has been discussed at the end of the lecture of today. So Hamilton, Jacobi-Bellman equations, and problems of optimal control. So we will revise everything in the weeks to come. Okay, but let's start with this today in here. And as you see, the idea of the 2 exercises that we're going to do is to start from data and estimate or model distributions based on the information that we have from sampling them and collecting data. So the setting is what I summarized in here. The idea is that you have a sample of data that I call Sn. So you have small n values of or realizations of your random variables. And in the course of these exercises, we are assuming that these data are obtained sampling independently, and I will comment on this at the end, but so far we stick to this framework of independent sampling from a distribution for the corresponding random variables, which is to some extent unknown. And the idea is to extract information about this distribution from the data that we had. So there are somehow 2 parts in this today. One is related to estimating, and the other one is what I call modeling. So let me give you a summary. I hope that you can see what I wrote in here, especially the colors. But you see that there are 2 things. So estimation is related to the first exercise that we are going to discuss, that is about maximum likelihood. Whereas modeling is more related to the second part, which is about maximum entropy. So what is the idea in these 2 cases? So in the first case, you are in a situation in which you are given a model. So what I call a model here is a functional form of the distribution from which you assume that your data are extracted. So you know what is the functional form of your row, but this row depends on a set of parameters which in principle are unknown. And the goal in here is to estimate these parameters based on the data. So there is somebody who is asking about where to find that it is. Okay, so there is a little bit of an issue, which is that with the ENS connection, I cannot enter into that folder, unfortunately. So I will have to guide you based on memory. But if you open the folder, you should find, I guess, a repository which is called M2. And then inside you find a folder which is called Complex Systems from Physics to Social Sciences. You click in there. You have subfolders, one of which is called TDs and Homework. And then you go to week 2, and in there you find the text of the second TD. So let me know. I see. Yes. So if anybody actually, let me do this. Let me send it to the mailing list. Okay, so now I sent the text to the mailing list and everybody should have it. Thanks for pointing this out. Okay, so as I was saying, in this case, what we need to do is to estimate the values of these parameters based on the data. So the input that we have are the functional form of our distribution, and we may have some prior information about how these parameters, or what are the properties of these parameters. We will see this in the exercise. And the output will be an estimator, so a value for this parameter that we get out of the data that we have. And so this estimator will depend on the particular sample that we have, and in particular will depend on the size of the sample. And this is why I put this little n in brackets, which indicates this dependence. So this is the way in which we are going to do this is through maximum likelihood, as I will explain in a minute. And then there is a second part, and the second part is about modeling. So in this case, we assume that we don't know even what is the form of our distribution, but we only know some constraints that this distribution has to satisfy. For instance, we know what should be the average of certain functions, which I call g of k, with respect to the distribution of the data. And the values of these averages may be given to you a priori, or you may get them directly from the data. And this makes a connection with this first part. And what are these functions? Well, in most of the cases, they are just the moments of your random variable. So you know, for instance, what is the average of your random variable, and you would like to find a shape, a form for the distribution that is compatible with the average that you have. And there are in principle many distributions which are compatible, so a whole family of those. And the idea is to use the so-called maximum entropy principle to extract or to give a good model for this distribution. So in this case, the inputs that you have are the values of these constraints, and the output will be the functional form for your distribution, which of course will encode the information that you have, and so it will depend on the constraints that you have. So this will be the topic of exercise 1, and this the topic of exercise 2, and then I will comment on what happens when you go beyond this assumption of independence. Okay, so let's start with maximum likelihood. So let me summarize a bit what is the idea in here. So this is maximum likelihood estimator. What is the idea? And first of all, what is the definition? So the definition starts from a basic formula in probability, which goes under the name of Bayes formula. And the idea is the following. So suppose that you want to compute what is the probability to get a certain value for your unknown parameters. So in general, you can have more than one parameter that is unknown. So I denote it as a vector. So this will be theta 1 up to theta n. And so you want to know what is the probability of this set of parameters giving the values, the sample that you have, so giving the data that you have. And using the laws of conditional probability, you see that this probability will be proportional. So the idea is that the probability of theta given x times the probability of x is equal to the probability of x given theta times the probability of theta. So this is what I'm going to write. So here in the right-hand side, I will have the probability of the set of data that you have given an assumption of on your parameter theta. And using the idea that the data are sampled independently from an unknown distribution rho, what this probability will be is just the product over all the data that you have of my rho of xi given a given value of the parameters. And then you have the probability for these parameters, which of course are unknown, but you can assume that you know something, some properties of those that you encode into some prior distribution, P prior, which depends on theta. And so in this language of Bayesian probability, this is called the prior. This quantity in here is called the likelihood. And what you have on the left-hand side, which is more or less what you want, is the posterior. And now what is the maximum likelihood estimator? Well, this is essentially the value of theta, which maximizes what you have on the right-hand side. And to make things a little bit simpler, we will maximize the logarithm, the so-called log likelihood, which is the logarithm of the right-hand side. So the value of my estimator, which is now a vector. So theta is a vector, and then I will put an at to indicate that this is the value that we estimate from the data. This is the maximum of a function that is a function that depends on the data that you have, and which is a function that in general depends on theta. And what is this function? Well, this is the log likelihood that, as I said, is the log of the right-hand side. So if I take the log of the product, this is just the sum from I going from 1 to n of the log of my rho of xi given theta. And then if I have some prior information, I have to add to this the log of this p prior over theta. So to solve the problem and get our estimator, what we have to do is to compute this log likelihood and then to maximize it to get the value of the theta. Now, let me make a few comments before we see this concretely in an exercise. So the first comment is that the problem that we are dealing with, or the setting, is essentially the one that one has in general in inference problems. So we are in an inference setting where we are assuming that our data are extracted from a real distribution. So we are assume that there is a real distribution that has the functional form that that we put into the model, but which has some real values of this parameter that I call theta star. So this is what usually is called the hidden truth. So we don't know what is the true value of these parameters, but of course, what we are doing in here is estimating this value from the sample of data that we have. And just as a notation in the following, I will denote with this expectation value, and I will denote with this variance the expectation value and the variance with respect to the true underlying distribution. So this is the average computed with respect to the rho, where instead of theta, I put the true value of the parameters, which is of course what we want to estimate. So as I said, from data we get some possible estimate for this set of parameters. Now let me assume, just for the notation, that we have one single parameter, so I don't have to use vectorial notation. So our maximum likelihood estimator will be some number. And what you can show is that this number or this estimator is consistent in the sense that if you take your sample to be of infinite size, so if you take small n going to infinity, you know that this will converge to the true value of the distribution from which you are sampling the data. So you have this sort of, if you want, kind of law of large number for your estimator. And you can ask, of course, how does this convergence happen as a function of your small n? So how does it happen? And what you can show is that it happens with fluctuations around the true value, which are Gaussian. So what I mean is that if you look at the rescaled variable, which is rescaled by square root of n, as you usually do in central limit theorem, for example, and you look at the fluctuations of your estimator with respect to the true value, what you can show is that asymptotically, so when n is large, this object will be distributed as a Gaussian. So we have a normal distribution, I denote it like this. And this Gaussian has zero average, and it has a variance that is related to a function E that is what people call the Fisher information. So this E in here is known as the Fisher information. And what is its expression? So let me try to squeeze it in here. So E is a function of your parameter, and it is minus the expectation value, now with respect to the true distribution, of what? Of the second derivative of the log of your distribution with respect to your parameter. Okay, and this you find also in the text of the today. So to characterize asymptotically your distribution, what you know is that in the limit of large n, your variance will be controlled by the value of this Fisher information at the true value of the parameter theta star. Now, of course, usually you are not in the very large n limit. So what you can ask is, what happens when your sample is maybe very large, but it is not strictly infinite? And in that case, what you can show is that the variance of your estimator is not exactly given by 1 over I, but it is lower bounded by 1 over I. So let me put it in here. This is the last formula that I give you before the exercise. So for finite n, what you have is that the variance of your estimator is lower bounded by 1 over n e of theta. Okay, so this 1 over n comes
so
from
that's not visible anymore.
You're right. Wait. Because of the screen and not because of, yes. Okay, now it's better.
Yes.
Okay, great. So of course, this is just telling you that if you look at a finite sample, the fluctuations that you get are larger than the fluctuations that you have in the asymptotic limit. But you still get an estimate of those looking at this Fisher information. So now we are going to look at all of this formula a little bit more concretely by solving the first exercise, and I hope that things will become even more clear. Okay, let me erase this. Maybe let me add a comment while I erase, which is that I wanted to stress that somehow the framework that you have in here is the one of an inference problem, because I guess that some of you have followed courses in the last semester, there was a course, for instance, by Floran Zakala that was about inference problems. And nowadays, this type of inference problems are becoming quite popular, even in research, in particular in the limit of large dimension. And this fits a little bit into this framework. And in that context, if you look at high dimensional inference and even problems related to machine learning, you will see these concepts of maximum likelihood, which emerge constantly in the literature. Okay, so now let's try to be more concrete and to look at an exercise. Maybe before, there was an example, so in the text of the today, and the example is, so I'm not going to solve the example, I just wanted to make a comment. So in that example, what you want to do is to estimate the exponent of a power law distribution using maximum likelihood, and this is related, if anybody had time to do the homework, is related to the homework 2. So the idea of homework 2 was to use this framework to try to fit data which are asymptotically power law and estimate what is the exponent indeed based on the data. And if you use this recipe of maximum likelihood, you end up with an expression for your estimated exponent mu that is of the form 1 over n sum I going from 1 to n of log of xi, which are your data, divided by xc. So what is xc? Well, what I'm doing in here is assuming that my distribution, rho of x, given the exponent mu, is power law, but it starts, so it's power law only asymptotically, so the power law starts from a given value of x, which I call xp. So you have to look at values that are larger than this xc. And what I wanted to point out with this example and with homework 2 is just that if you use maximum likelihood, you get this estimator, which is called the Hill estimator, which depends on this particular value of xc. So when you try to fit and estimate powers from data, there is a little bit of sensitivity with respect to this parameter that you have to choose. So you have to play around, change a little bit this xc. If you don't have, of course, an exact power law, but data which are only asymptotically power law, and you will see that your estimator changes. But the good choice of xc is signaled by the fact that once you get it and you vary a little bit the value of xc, you find that this quantity doesn't change much, and therefore you have a good estimate of your exponent. So if you want to look at an example concretely, this was given, this was the idea of homework 2, where we use this to estimate the power law of the distribution of words in language that we saw in the homework number 1. Okay, but this is just a parenthesis. So now let me go to the 2 exercise, and maybe I will erase this to have space. So in this exercise 1, the setting is as follows. So we assume that our data are taken from some Gaussian distribution of which we don't know either the average, the mean, and the variance. So our rho of x will depend on this unknown parameter, the mean, which I call m, and the variance, let me call it b. So this is sigma squared. And this has a Gaussian shape. So this is 1 over square root of 2 pi v e to the minus x minus m squared divided by 2v. So m and v play the role of my theta in the formulas above, are the parameters that we want to estimate. And we have some prior information on both m and v. So for m, we know that, or we assume that this is distributed a priori as a Gaussian with some variance capital sigma and with 0 average. So the prior will be e to the minus m squared over 2 capital sigma squared divided by square root of 2 pi capital sigma square. And for the variance, we assume, or we have, at the beginning, we have good reasons to believe that this is distributed as an exponential, so e to the minus v lambda divided by lambda. Okay, and now we just want to apply this recipe to get estimates for these parameters. So of course, the first thing, I hope you can see if I do this, the first thing that we have to do is to compute the log likelihood. Okay, so what is the log likelihood in this case? Well, what we have to do is to take the sum over all the data that we have of the log of this distribution. And now I will use the fact that eventually what I want to do is to take the derivative of this object with respect to m and v. So I write down explicitly only the terms which depend on m and v, and all of the other terms, I will collect them into a constant because they don't matter when I look at the derivative. So if I do this, I get the first term, which is the logarithm of this. So I get a minus sign, which comes from the exponential. So it's minus xi minus m squared divided by 2v. Then I have the logarithm of the normalization. So I just keep the factor of v, and this gives me minus 1/2 log of v. And then I have the logarithm of these prior distributions. So the first one will give me a factor of minus m squared divided by 2 capital sigma square. And I can neglect the normalization because it does not depend on m and on v. And from here, I just get minus v over lambda. And then all the rest is collected into some constant, which depends on sigma and lambda. Okay, so this is my likelihood. Now this depends on 2 parameters, and I have to take the derivative with respect to both. So let's start from m. Let me take the first derivative of the likelihood with respect to m. So why should I take the derivative? Because I want to maximize. So I look at stationary points. And if I do this, what do I get? So I have a minus in here that will cancel from the minus, with the minus coming from the derivative over m. So I'm left with sum from I going from 1 to n of xi minus m. I bring down a factor of 2, which cancels with 2, so everything is divided by v. And then the other term is this one, and this will give me minus m over sigma squared. Okay, now what can I do? I have to solve for m, so let me multiply this by v. Okay, and let me do the following. So this is a sum of a term which depends on I and a term which does not depend on I. So I can just sum over the second one, and this will just give me m times small n, which is the number of terms on which I'm summing. Let me divide by small n. This is just algebra. Okay, and now let me solve for n. So if you do this, what you get is that m is equal to what? Is equal to 1 over n sum 1 over n xi divided by a factor which is of the form 1 plus v over n capital sigma square. So what you see is that in the numerator, what I have is essentially the sample average of my sample Sn. So I will just denote it as the average of x over the sample. And then I have this factor in the denominator, which contains the information on the prior distribution through this sigma square and through the variance that we have to fix taking the second derivative. Sorry, not the second derivative, but the derivative with respect to v. Okay, so this is the first. This will be our estimator for m. And now what we have to do is the same thing, now taking the derivative of this guy with respect to v. So let me just sketch it. we will get a second order equation. So, okay, from here, the minus cancels and I get sum I going from 1 to n, xi minus m. Let me know if you don't see what I'm writing. So I have 2 over v squared. Then the logarithm, which gives me 1 over 2v. And then what do I have? I have this one, which gives me a factor of 1 over lambda. So let me multiply this, since I have to set this equal to 0 as above. Let me multiply by v squared. So here I will have a factor of v, and here I will have a factor of v squared. And this has to be equal to 0, so I have to solve a second order equation. So I just write the result. To save some time. You can do it while I erase. So if you solve this, you will see that your estimate for v is of the form n lambda divided by 4. Then you have a minus 1. And then you have plus square root of 1 plus 8 over lambda n square sum over I from 1 to n of xi minus, here I have m, so I replace it with my estimate to the power 2. Okay, and I have to choose the plus sign because I want the variance to be positive. So here I have a minus 1, so I have to add something which is positive to it to get a positive variance. Okay, so this gives us the expressions for the two estimators. And of course, in this v here, you have to replace it with v hat. So these are coupled. And now let's go to the second point. So this was point 1. And the second point is about what happens when we take the limit of the sample small n going to infinity. So we have to take the limits of these expressions. So the first one is pretty easy. So you see that the only dependence on small n is in the denominator, and this is such that if you send n to infinity, you get you're left only with 1. So this means that in this limit, your estimate for the average is just the sample average based on your data. So the dependence on sigma disappears. And what happens for the variance? Well, something very similar happens. So how do you take the limits here? You see that when n is large, this object is small. So you have 1 plus something small to the square root. So this you can approximate as 1 plus 1/2 times the small thing. This is just Taylor expansion. And if you do this, the 1 cancels, and you will see that you cancel 1 factor of n, and you're left with something very simple to expect, which is that this is just the sample variance that I will denote as x minus, let me say, m hat averaged over all of your data. And this is something that is good and that you may expect. So what this is telling you is something that you can summarize as the expression that evidence takes over. So what this is telling you is that you had some prior guess of what were possible values for m and for v, given their distribution. But in the limit in which your sample becomes infinite, the information about this guess becomes not relevant, so it disappears from your expression, and the only thing that you're left with are the data. So in the limit in which n goes to infinity, evidence, which means the information which is contained in your data, becomes the only relevant thing to estimate these parameters, and you can forget about your prior information because your data are enough to give you information about the structure of your distribution. And this is the same thing. So you,
sorry.
Yes, thanks. And what I was saying is that this is exactly the same thing that you would get if you had no prior information at all, which is consistent with what I just said. So no prior information would correspond to the limit of this expression in which sigma goes to infinity and lambda goes to infinity. So that basically your Gaussian and your exponential becomes kind of flat. So you have no information a priori on what is the distribution of your parameters. And in that case, the only thing that you have are data. And so you get that your estimators are precisely just given by data. Okay, so now we are going to use this case of no prior information to comment a little bit on this Fisher information and on this bound, which is called the Kramer-Rao bound on the variance of your estimators. And this concludes the exercise. So where should I do it? Let me do it. Well, maybe this is useful. Let me do it up here. If it is not clear so far, please stop me anytime. Okay. So let's go to point 3. And point 3, I think it tells you the following. So suppose that now we know that our average is equal to 0. So we know that this, we can set it to 0. And we have no prior information on our variance. And therefore, based on the equation that I just erased, our maximum likelihood estimator for the variance is just 1 over n sum over our data of xi squared, where I don't have to shift by the average because I assume it to be 0. And now what we want to do is to compute the left-hand side of this inequality. So you want to compute the variance of this estimator with respect to the true distribution. And what is now the true distribution? So we are assuming that this is Gaussian and it has a true value for the variance, which I call now V star. So it is just 1 over square root of 2 pi V star times e to the minus x squared over 2 V star. Okay, so let's compute the average of this estimator with respect to this distribution. So as I said before, I denote it like this expectation value. So I have to compute the expectation value of this sum. Sorry, the variance. Now I use the property of the variance. The variance of a constant times your random variable is the constant square times the variance of your random variable. And moreover, the variance is linear. So the variance of a sum is the sum of the variances. So what I get is, using that my distribution is Gaussian, I get a factor of 1 over n. So it would be 1 over n squared coming from this, and then an extra factor of n, which comes from the sum. And then I have just the variance of my random variable x. And this is what? Well, this is 1 over n, the expectation of, sorry, this was x squared. So this is the expectation of the object square. So this will be x to the 4 minus the expectation of the object to the power 2. I'm just using the definition of the variance in here. And now I want to compute this expectation with respect to the Gaussian distribution. And I use, to compute this expectation of x to the 4, I use a property of the Gaussian distribution, which tells you that all of the moments which are higher than 2, I can factorize them into products of the expectation values of x squared. So this is what is usually called in many contexts as the Wick theorem. It's a property of Gaussian measures. So if you do field theory, you will see this emerging many times. So this is a simple example. The idea is that to compute the average of x to the power of 4, you can write it as the sum over all possible contractions in which you take two values of x and you compute the expectation, and this is factorized from the contraction of the remaining two values of x. So what you find is how many ways you have to pair these four elements into couples of 2. Well, you have essentially 3 ways. So either I pair this one with this, or this with this, or this with this. So what Wick theorem tells me, or if you want just properties of the Gaussian, you can compute it, is that this will be equal to 3 times the expectation value of x squared, which is one pairing, times the expectation value of the other pairing. So this is just 3 times the expectation of x2 to the power 2, which combines nicely with this. So in the end, what we find using this trick is that our variance is what? Is 1 over n times twice the expectation of x squared with respect to our Gaussian distribution. And this is just the variance to the power 2. So this will be v star to the power 2. Okay, so what I hope this is fine. Anyway, or in any case, just stop me. But this is basically what you have on the left-hand side of our Kramers-Rao bound. And now let's try to compute for this particular example what is the right-hand side. So what is the Fisher information, and see what we get. So let me erase maybe this part. Okay. So this is the last point. And the last point is asking us to compute now E of V, which is our parameter. That is, as I said, minus the expectation value of the second derivative of the log of rho of x given p derived over v. Okay. So before we do this computation, there is a question in the exercise, which is, let's say, let's try to give an interpretation to this Fisher information. And the idea is that you can interpret this Fisher information as a measure of how much your model, so your distribution, is informative. So, and indeed, this is what the name is suggesting. And why is it so? Well, if you have no prior, what you see is that this is a second derivative. And if you just have the first derivative, what you are taking here is basically the first derivative of your log likelihood. So it is what you should set to 0 in order to fix your maximum likelihood estimator. And then you take the second derivative, which tells you about a fluctuation, so about how much this function changes if you change the value of v. And the idea is that your distribution is very informative if let's say, fluctuations are large. So this is telling you that it is quite easy to locate what is the true value of V, because as soon as you move away from the true value of V, your let's say distribution is changing a lot, and this is measured. This type of information is measured by an object like this, and this is why you see that in this inequality, the Fisher information appears in the denominator. So the idea is that the larger it is, the smallest is your lower bound, and therefore the more hope you have that the variance of your data is small. So if you instead have a very small Fisher information, this is telling you that the shape of your distribution is not very informative, and so you will know for sure that the variance of your data will be larger than some threshold which is sufficiently much larger than 0. So this is why this is called information indeed. And now let's see what this gives us in this case. So what we have to do is to compute the second derivative. So let me maybe just do it quickly. Where is it? Okay, this I just said. Okay, very good. So if I do this computation in here, now I hope that with the factors of n I'm fine. So what I get is, okay, so where is my likelihood? I erased it. Oops, so I will just give you the results. So my likelihood derived with respect to V. So now this is as an extra factor of small n, but just to link with the notation above, this was given in the case where you have no prior, so when lambda goes to infinity, by something like this, minus n of the 2v. So this comes from the logarithm of the distribution of m, and this comes from the Gaussian term. And then if I take the second derivative of v, what do I get? So now I have no space. Okay, this will be, so I get a factor coming from here. This was a square, sorry. So I get a minus xi square over v cube. And then the derivative from here will give me my n over 2 v square. Okay. And what is this? Well, this is essentially n times the Fisher information that I wanted to compute. Why n times? Because I'm summing overall values, overall possible values of my data. And this gives me this factor of n. So in a nutshell, sorry, this is not yet EV. This is n times the second derivative of 1 log over v square. Okay, so now to get EV, what I have to do, I have to divide by n, and then I have to take the expectation of minus this object in here. So EV times n is nothing but minus the expectation of this object up here. So the expectation of the first term is 1 over v cubed times the expectation of x squared, and then I have a factor of small n. And the expectation of the second term is easy. This is just a constant, so this is n over 2 v squared. And so you see that this will give me an extra factor of v. So I will have, and I add a minus that I didn't account for. So I will have n over v squared minus n over 2 v squared. So the result is n over 2 v squared. And this is n times the Fisher information. Okay, And so what do I see from this? Well, what I see is that if I now compute the right-hand side, so what I just gave in here, at the true value of v, I just get 2 v star to the power of 2 divided by n, which is exactly what we got in the left-hand side. So this is an example in which actually the bound that you see up there is saturated in this case. And whenever this happens, people say that the maximum likelihood estimator is efficient. So this is the terminology that you get. So let me write it here. In this case, your estimator is efficient, meaning that you get a bound which is no longer a bound. So you really know, computing the Fisher information, what is the variance of your finite n sample. Okay, so I hope this was more or less clear. Apart from these factors of n which were fluctuating, but I hope now it's fine. So are there any questions about this exercise? And if not, I think we can jump to the second case, which is about modeling, so computing distribution based on maximum entropy. Okay. And then I will conclude with a comment on correlation. Okay, so maximum entropy, I think you have encountered it several times. It is one of the ways, as we will see now, in which you justify the emergence of Gibbs distribution, for instance. And the idea is as follows. So this is now maximum entropy. This is the idea. So the idea is that you want to get a distribution that I call rho maximum entropy of your random variable x by maximizing something, which is the entropy. That is a functional of your distribution that you recognize from any physics course. So this is a functional because it is a function of the full distribution, which is itself a function. So here I'm denoting the variable to which it refers. And this is just minus the integral of rho x times the log of rho x. And you want to maximize these objects, but in a way which is compatible with the constraints that you have. So let me rewrite it. So this is subject to constraints, which I wrote in the following form. So we know what is the value. So this barring here is just a notation. It's just to tell you that this is a number. And it is indeed obtained as the average of the corresponding function over your distribution. And the prescription to do this constrained maximization is, as usual, to use Lagrange multipliers. So via the so-called Lagrange method. So I will review it now. And what do you get out in this type of calculations? Well, you always get out shapes for this distribution that are of the exponential form. And the reason is that you have a logarithm here, and this is what gives you exponential shapes. So let me show this very quickly with an example. So first of all, how many constraints do you have? Well, you can have many. So let me say that my index k goes from 1 to capital K in general. Okay, so let's do then the first 2 points of the second exercise, which is just an example of this. So the idea is to show that if you are in such a setting, the outcome of such a maximization is of the following form. So you get a distribution rho of x, which you can write as e to the some constant, which accounts for the normalization. And then you have a sum over all your constraints, so from 1 to capital K, sorry, of some parameters, which are your Lagrange multipliers, as we will see, times the function itself. So why do we get this? Let's show this. So what we have to do is to maximize this object, and this Lagrange method means that you introduce some modified version of this functional that depends on other Lagrange multipliers. So now let me introduce a lambda 0 and a vector mu, and the vector mu collects all of these values in here. So this goes from 1 to mu capital K. And this new functional is the functional of before, so your entropy. Then you add the constraints. So the constraints are the sum of your Lagrange multipliers times what you want to enforce. And what you want to enforce is that the average of your functions take the given value that you are given as input. And you have an extra constraint, which I impose with a multiplier lambda 0, which is that you want your distribution to be normalized. So you want that the integral of dx rho of x is equal to 1. Okay, so let's maximize this. So let's take the derivative of this with respect to the distribution rho. So this is the functional derivative of this object, which I denote like this. Lambda 0 mu with respect to rho. So if anybody is not familiar with functional derivatives, we will use them also in the next TD, by the way, but the idea is it works exactly as a derivative where you essentially derive with respect to the full function. So for instance, I will show it with a concrete example and it will become clear. So the first term that I have to derive is just the entropy. So this is rho times log of rho. So the first derivative will eliminate this factor of rho. So I'm left with minus log of rho of x. And then I take the derivative of rho of x. It gives me a 1 over rho of x, which cancels with this. So I have an extra factor of minus 1. And then all of the other terms, they are linear in rho of x. So what I obtain is a sum over all values of k of mu k gk of x from here. And then from the normalization, I have a factor of lambda 0. Okay. And now in order to recover, so this, I have to impose this to be equal to 0 because I want the maximum. And you see, I introduced lambda 0 because I just wanted to call mu 0 as lambda 0 minus 1. So I absorb also this constant. And if you solve these equations equal to 0 for rho of x, you get out exactly the type of expression that you see in here. Okay, so this gives you the exponential shape that, as I said, comes from this logarithm. But there is something more which you have to do because, of course, now these multipliers are not defined. So you have to fix the values of these Lagrange multipliers using the constraints that you have. So let's do it quickly. So the value of mu 0 comes from normalization. So what I have to do is I integrate that expression for rho over x, and I set it equal to 1. And this tells me that e to the minus mu 0 is equal to the integral over dx of e sum over all my values of k of mu k times gk of x, right? So this is an equation for mu0 that tells me that mu0 will be a function of all of the other values of mu, given by these implicit relations. And then what is the equation that I get for each other value of mu? Well, what I have to do is to rewrite this constraint in here, plugging the expression for my maximum likelihood density. And so what I get, so let me do something which will resonate with you. Let me call this Z, like a normalization in a partition function. And what I will get out of the other constraints is that G average K is what? Is 1 over Z, so e to the mu0, times the integral over dx of just G over X e to the my sum. Okay. And this is what fixes all of your Lagrange multipliers. And as you see, this is basically what you do. So this is very reminiscent of what you do when you do basics of statistical physics. So the idea is that, for example, in statistical physics, you may interpret your X as a configuration, and the constraint that you may have is, for instance, the value of the average energy. So let me write it as a comment. So you may choose your just one value of K, and you may choose then your function to be the energy as a function of the configuration. So I will now call it small h. And then what you have is you have a certain value of the average energy, and what you are looking for is a distribution which is compatible with this average energy. And out of that formula, what you get is precisely a distribution of the Boltzmann form. So you will get that rho of x is of the form 1 over z e to the mu times h of x, where mu plays the role of minus beta in the usual physics notation. And what is mu0? Well, you can identify from this type of relation, mu0 is essentially the free energy of your system, and this type of equation gives you the usual relations between indeed the energy as a derivative of the log of the partition function, so of your free energy. So you recover everything from this framework in here. And you can go beyond this. So of course, in this case, you just have one multiplier to fix, but you may have several constraints to impose. And in this way, you will get out expressions that are some sort of generalized Gibbs ensembles. And now these are also becoming very popular, in particular in contexts which are a little bit different of quantum mechanics and integrable systems. So if you're interested, I can give you some references about this. And the last comment to connect with statistical physics is related to the point 3 of this exercise, which I leave you as an exercise. So out of this formula, you can show that you can recover some relationships which are very well known in equilibrium statistical physics, so for Boltzmann-like measures, which are known as fluctuation dissipation relationships. So this is just algebra, but it is nice to see the connection. Okay, and now I just wanted to conclude with the last part. So I hope this this is clear. And the last part is to connect a little bit between maximum entropy and maximum likelihood. And this is the point 2 of this exercise. And what we do in this point 2 is to assume that now we are given, so now we go back to the context of estimation, so of maximum likelihood. And we assume that somebody gives us our distribution that is of the form above, so derived in this way, but with parameters which are unknown and that we want now to estimate based on data. So in this case, the shape of the distribution is, let me rewrite it. I have a normalization which depends on all of the other constraints. So I indicate this dependence explicitly, and then I have some k going from 1 to capital K of my mu k gk of x. Very good. And now I want to use this type of distribution in my maximum likelihood framework and see what comes out as an estimate for these values of mu k. And this is a simple exercise in here. So I assume that I have no prior information on these parameters mu k. So what do I have to do? I have to compute my log likelihood, assuming that I have a sample. And my log likelihood, as we saw before, is the sum overall of my data of the logarithm of this distribution computed at the particular value of x, which I find in the sample. And so this will be, I have a first term coming from here, which is mu k gk of xi. And then I have the constant term, so I collect the factor of small n, and I have mu0 of n. And now to minimize this with respect to, I have to minimize this with respect to the mu k. And so the equations that I get, the estimate for my mu k is what? Okay, so I will get from here. Okay, let me write it implicitly actually. So if I derive this, what I obtain is n times the sample average of my gk. Now I'm deriving with respect to one particular value of k. So this will select only one element of this sum, and I'm left with a second sum over I. And on the right-hand side, I have to remember that this normalization depends on all of my parameters mu k. So I have in here a derivative of mu0 of mu with respect to d mu k. And this, I have to impose it equal to 0. So you see that this gives me the following equation. So I cancel a factor of n, and I bring one to the other side, and I get these equations. That is very, very similar to the equation. So this is now an implicit equation for my values of mu that will be fixed with maximum likelihood. And the expression is very similar to this type of equation, which fixes the values of your parameters with maximum entropy, except that now your left-hand side is not some number that is given to you a priori, but it is some number that you get out of the data. So it is now the average of your function g with respect to the sample of data that you have. Okay, so this is to make a connection between the two things of today. And I wanted to now conclude with a couple of comments. Okay, so first of all, why the expression are the same? Well, because you know that you can rewrite this object in here as the derivative of the log of z with respect to mu k. You can show this equation. So this will be equal to the derivative with respect to mu k of what we call log of z, but log of z is what? Is log of e to the minus mu0. So here you will get a factor of minus mu0. That is precisely what we have on the right-hand side. Okay, so that's all for the exercise. So let me now go to some final comments, and then maybe we can also comment on the third exercise very briefly. And this final comment is to give a little bit of perspective and connect with some of the things that will be discussed at the end of the course. And it is about correlations. So if you remember, what we assumed and stressed at the beginning is that we always assume that the data that we have are obtained sampling in an independent way from a given underlying distribution. So now we can ask, what happens when instead we have data that are extracted from a process which has some correlations. So what is the setting in this case? So in this case, we can assume that we have not just one random variable x, but we have more random variables. So let me collect them into a vector x. So this will be, now I label them with a superscript, and let's say that we have, I don't know, m of these random variables. And our sample will be given by realizations of all of these vectors. So I will have a set of numerical values for each of these entry of my vector. And the different values are labeled by I, and I have small n of those. Okay, so now I'm sampling n times each entry of the vector. But I am assuming that somehow these variables which make the vector x are correlated. And in particular, I assume that there are pairwise correlations, for example, between these variables. And then I can try to repeat this scheme with maximum entropy, this recipe, to find a shape for the distribution of these objects. And I will tell you what is the result that you should get and just comment on this. So first of all, we have to introduce, as before, an average over the sample, but now we have capital M averages corresponding to each entry. So what is this? This is 1 over n, sum I going from 1 to n of all of my realizations of the variable xi coming from data. And we can also introduce correlations between pairs of the components of these vectors computed on the sample. And this will be, as you expect, the same sum as above. Okay. And if you repeat the kind of reasoning that we gave before for the simplest case, what you get is that in this case, the distribution given by maximum entropy, which is now a distribution, a joint distribution of all of the entries of your vector, takes the following form. So you have some normalization factor, which is the same as e to the minus mu 0. And then you can write it as sum over alpha, which goes from 1 to capital M, of some multipliers that now I call H alpha, just to be reminiscent of some physics notation. So far, if you have just one value of M, is precisely what you would get as above if you choose just one value for the function g that is a linear function. So if you just know what is the average of x, you will get a distribution that is of the form e to the mu times x, following the scheme above. But here, since we also have correlations, we have a second term, which is the sum over all pairs xa, xp with some other Lagrange multipliers, which depend on both indices, and so which I denote as j, ab. And how do we fix h and j? Well, following the same ideas, what you will find is that you have to use the average of the sample, and you will have an implicit relationship between your sample average and the shape of this distribution of the following form, where now you integrate overall values of x, and similarly, your sample correlations will give you an equation, implicit equation for the J that looks like this. Okay. And I just wanted to comment that what you end up with in this type of framework is some inverse easing problem. Well, I call it easing, but you know, these couplings can also take arbitrary signs and so on. But as you see, this is the shape essentially of the partition function of an easing model with some local fields. If I interpret each values of x as an entry or as a spin, if you want. And the problem that you have to solve is not the usual problem. So in the usual problem, you are given the couplings of your Hamiltonian, and you want to compute correlations out of these couplings. You want to compute the partition function. You want to compute the average energy, and so on and so forth. Whereas in here, we are given the shape of our distribution. We don't know these parameters here. We know some of the correlations from the data, and what we have to do is to solve for the parameters given the correlations. So in this sense, it is an inverse easing because, as I said, you do not know the couplings of your Hamiltonian, and you want to infer them based on the statistics of the data that you have. And this is a problem which comes out in many, many settings. So you will find it in statistics, in biology. Maybe if you follow the course of Rémy Monasson, you will also see this appearing in there several times. And perhaps let me add the last comment to connect with the last day about correlations. So at a certain point in the last day, I asked you, so there was a discussion about real language versus random language. And we commented on the fact that our model for random language, it was giving us a zip flow, which we could compute explicitly, but somehow there were assumptions that were not very realistic. And in particular, one of the assumptions was that any sequence of letters was an acceptable word in the random language case. So the total number, I don't know if you remember it, but we said that the total number of words of length of a given length L was just given by M, which was the number of letters, to the power L, which means that we accept, so we have just to count how many combinations, how many strings of length L we add, and we accept all of those as admissible words in real language, in a random language. But of course, in real language, this is not the case. So we know that AKL is not a word. So there are some rules of selections of words, and you can think about these rules as being encoded into correlations between the different letters. So this is just to stress that in any context that you are thinking about, and in any realistic models, correlations will matter, and problems of this sort will appear anytime you try to model them based on real data. Okay, so I think it's time to stop. So the third exercise is it goes back a little bit to things that were discussed in the previous lectures about freezing and power laws and estimating the maximum over a set of variables which are power law distributed. So there are some nice ideas in there, but I think you can look at them with the solutions, and then if there are issues, write on the question and answer file, or we can discuss them during the next day. So are there any questions about this? Otherwise, I will just say something to conclude for those who are still online. So we have been said that there is the possibility to have some people in class during the lectures and during the today, but the number of people that can stay in the room is only 2. And therefore, so I think this might be a good thing for those of you who want to move a little bit and come to ENS, but we have to decide who wants to do this, and if there are more than 2 people, we have to somehow do coordination to decide who comes each week. So if you're interested and you would like to come physically, just send me an email and we will try to organize this for the next weeks. Okay, any more questions or comments? Was it fine? I can stop the recording.